Okay. Now that you've seen or you understand what is the origin of trigonometric ratios and where do they come from and how do they relate to similar triangles, in this section we are going to have a short video where we look at evaluation of trigonometric ratios for two special angles. Now those angles are, we are going to write two angles, and that those angles are 90 degrees and 0 degrees and 0 degrees. So we'll try something very special. We'll see here. Sorry about that. We'll try something very special and very exciting. Try and make this as very exciting as we possibly can. So here's our right angle triangle. Remember that our angle of special focus is this angle and that angle there, and then this 90-degree angle here. Right. Now, from this right angled triangle, we are going to be focusing on theta, this side. We can forget about alpha, and we already know that if this is focusing on theta, this is our opposite side, this is the adjacent side to theta, and that's the hypotenuse. If we were focusing on that angle, this would be the opposite, and this would be the adjacent to that angle. But we are having special attention to this theta. Now, we want to look at 90 degrees angles. So, let's say for some special, we want to look at 0 and 90-degree angle. Now, let's say for some special occasion, the angle of our focus here, angle theta is equal to 90, and the case where angle theta is equal to 0. We're going to start with the case where angle theta is equal to 0. Now, we want to look at all our trigonometric ratios for that case. Remember that we have SOHCAHTOA, and then from SOHCAHTOA we have sine of theta is equal to opposite over hypotenuse, and we have cos of theta is equal to adjacent side over hypotenuse, and then we also have the tangent in relation to theta, which is tan is equal to, in relation to theta is equal to opposite SOHCAHTOA, opposite over adjacent side. So from looking at this, we can see our adjacent side and we can see our triangle there. So I'm going to make an evaluation here. I'm going to make a nice example here. So let's look at an example on this side. So let's look at these angles and how they really work for us. So what we're going to do is that we are going to write this here in this format. We are going to write it in this format. Oh, my drawing skills. We are going to write it in this format, right? Like this. And somehow just keep this line dotted and not have it. You can keep it dotted, this, not really have it, and then we can focus on our angle theta then. Now, I want us to look at a case when that angle is theta. What does this mean for this triangle when that angle is 0? Now, in this case, because my triangle is facing this direction, we are going to be measuring our angle from this side. For now, don't worry about, we are going to be measuring our angle from this side. For now, don't worry much about the directions of measurement of angles and what they mean. Okay, just know that we are going to be measuring our angle from that side. So we are measuring against it, what? We are measuring it against this line, right? So when this line there, let's say maybe when we measure this angle, when we are here, we know that when we are here in this sense here, this is 90 degrees. We know that when we have this straight line here and we're looking at this angle here, that is 90 degrees. 90 degrees when these two lines are perpendicular to one another, straight and cutting each other perpendicular. That is 90 degrees. And then we can again go and look at another feature and say when we have this line here, okay, let me take that one. When we have another line, can I get more features, more colors here for illustrations? Yes. So when we have another line there, that could be maybe for that line there, that could be 60, and then we get another line, brown line, maybe around there. The angle is starting to get smaller, it's becoming 30, and then as we move along again here, it gets smaller, maybe it becomes 10, and then we draw another line again. It becomes even smaller. The angle becomes even smaller, and it becomes maybe 3 degrees. So as you can see that as we start moving this line in this direction and start moving it down and down and down and down, this angle here, which is the angle theta we're focusing on, is becoming smaller and smaller and smaller and smaller and smaller and smaller. So as this angle becomes smaller and smaller and smaller, what is happening to the opposite side? It's becoming smaller and smaller and smaller and smaller and smaller also. So we start like this triangle very big, right? Then we get another line and it gets smaller. The angle gets smaller. We get another line again. Let me use brown. Let me use red. Red looks nice. We get another line. Oh, we can use this one, orange. We get another line again, and it becomes even smaller. So do you see that when we started, our opposite side was there. We moved a bit, the angle, it became, this was our opposite side. We moved the angle again, now this is our opposite side. So that was very huge, then this was smaller, then that is even smaller. So you're noticing a trend here that as we move towards 0 degrees, this opposite side for this triangle is becoming smaller and smaller and smaller and smaller in relation to theta, which is the angle of focus that we're looking at. Now, we can go further here and look at this much further. We can see that when we are at 0, this line here of this angle is going to be lying on top of this one. There won't be any separation between these lines from that corner where they meet. They will be exactly on top of one another, meeting at some point and moving exactly on top of one another. So that's going to be the angle 0. So in a sense, I'm going to make it like this. So we have the baseline, right? And then when we are looking at the angle, and then we have the baseline, and then on top of that baseline, we have a small line. That's when we're at 0. So they meet at that vertex there, and then they move on top of one another. So there's no separation in between them. And because there's no separation in between them, the opposite side is 0 also. When there's a separation in between them, when they meet there, and then you get a line like this, then there is separation between them, which means the angle there will be maybe 5 degrees or whatever it is, and there will be an opposite. But at 0, there is no opposite side. So we can see that in any right angle triangle, we can deduce a very nice analogy here, that in any right angle triangle, when theta, the angle of argument, is equal to 0, then the opposite side is also equal to 0. The opposite side to the angle theta will also be 0. Now we want to go and look again. This was for 0 degrees. Now we are going to go and look at 90 degrees. At 90 degrees, we can do the same thing. But then now, instead of moving in this direction, we are moving from this side to that side, right? So we start with these 2 lines laying on top of one another. Here again, start with one line laying on top of one another. They are meeting there. That there is the vertex where they are meeting, but they are laying on top of one another, and the angle is 0 degrees. And then we start increasing. We start moving, increasing up, and then as we start increasing up, we get a value. We increase up again. We get another value, and then as you can see that as we increase, the opposite side is becoming bigger and bigger and bigger and bigger and bigger. And we're going to keep on increasing and increasing and increasing and increasing. But once we reach 90 degrees, what is going to be happening is that this triangle is going to kind of blow off and no longer be really a triangle. Like there, we just had 2 straight lines. It's going to form something like this. So it will blow off. So in a sense, we won't have the adjacent side, because our triangle is supposed to be like this. Our triangle is supposed to be like this. Our triangle is supposed to be like this and like this, right? Okay, I think I made something very bad here. Okay, but it's fine. So we have this side here, which is the opposite side, and then we have that there, and then we have theta here. And then we're saying we keep on increasing theta until theta is 90 degrees. until theta is 90 degrees. We keep on increasing theta until theta is 90 degrees. Now if we keep on increasing theta, sorry about that. Now if we keep on increasing theta until theta is 90 degrees, you are going to notice something here that in a sense we go and go and go and go and go and go and go like this. And in a sense, the hypotenuse will keep on moving and moving and moving and moving like this until it becomes exactly equal to the opposite side. So the adjacent side would be there. Another great way of making this example is by using that side there, that angle there. So we are looking at this and we are looking at that angle there. So as you keep on increasing this here, as you keep on tracking this here, this side, tracking this here, this side, what is going to happen is that the adjacent side is going to start getting smaller and smaller, because in a sense we can say we are measuring in reference to that line there. We can measure this angle also in reference to that side there. And as you keep on making this, tracking this angle there, tracking this angle there, tracking this angle there, the opposite side here is still remaining open. That's still the opposite side, because that side there, we can draw this triangle like this, have two triangles like this. So that side there and this side here exactly equal. And as you keep on moving and moving and moving and moving like that and becoming smaller and smaller and smaller and smaller, as you can see that the hypotenuse is slowly moving and moving and moving and moving until it exactly equals the opposite side, which means the adjacent side. In a case where it's like this, we can say it becomes 0. So we can say in a case of 90 degrees, in a case where theta is equal to 90 degrees, the adjacent side becomes 0. Some people can say it becomes infinity, it doesn't matter, the adjacent side becomes 0. But I hope you get the idea. Like I said, I like proving these things intuitively, and with analytics, some proofs might be different to this. You might try different ways. If someone doesn't understand it, I might teach it a different way, find another way of explaining it. That's the nice thing about mathematics. As long as it's consistent and truthful within the axiomatic nature of mathematics, is fine. So this is what we have seen in this sense, that when that happens, your hypotenuse, in that case, when theta is 0, your hypotenuse goes down and goes down until it lays on top of the adjacent. In this case, your hypotenuse goes up and up until it lays on top of the opposite, making the adjacent basically non-existent. So then, what does this mean then, having these opposite sides and this being 0? Virtually a triangle that is very hard to imagine. We're having this triangle that is very hard to imagine. So remember, we talked about those them. We talked about those ratios them. But we're saying now, yes, we do. We're saying now for the case of 0, for the case of theta is equal to 0, theta is equal to 0. So this is case 1. Case 1, theta is equal to 0. So for the case of theta is equal to 0, we are saying that the opposite side virtually goes to 0. The opposite side virtually goes to 0 in relation to the angle that we are referring to. And then what's going to happen is that when we take the cosine, the sine of 0. So remember that sine of 0, our angle now is 0. So it's sine of theta, but theta now is 0. So we're saying sine of 0 is equal to opposite over hypotenuse. Opposite over hypotenuse, our opposite over hypotenuse, but our opposite is what? Is 0. So it's 0 over hypotenuse. So whenever you divide 0 by a number that is 0, so you will see, so then sine of 0 will always be 0. Remember that we said these ratios are the same and it's dependent on an angle. And the trigonometric ratio of a certain angle will always be the same. It doesn't matter how big the triangle, how small the triangle is. That's what we're developing when we're looking at similar triangles. We can go again to another. We can go to cos and say cos of 0. Remember, we said that in the case of cos, we said that in a case where theta is equal to 0, cos comes and lies exactly on top of the hypotenuse comes and lies exactly on top of the adjacent, so they become equal. So in a sense, we can say this becomes adjacent over hypotenuse, but because they are equal, then whatever value you get there, if adjacent is 17, this would be 17. If it's 20, this would be 20, because this moves until it lies exactly on top there. So then this becomes 1. Cos of 0 becomes 1. And then for a tangent, remember tangent, we're saying this is opposite over adjacent. Then this means that our opposite in this case will be our opposite will be 0, and our adjacent will be a value. So in a sense, it's also going to be equal to 0. So so tangent of 0 will also be equal to 0. And cos of 0 is going to be equal to 1, and sine of 0 is going to be equal to 0. So I hope you get this. And we can go also to the case of 90, and we can say we have case 2, we have case 2, we have case 2, and then in case 2 we have cos, we have sine of 90. We have in case 2 we have theta is equal to 90, and in that case the adjacent is equal to 0, and the opposite side exactly becomes equal to the hypotenuse, because they just have two lines that are lying on top of one another. This, yeah. So sine of 90, in a sense, then in this arrangement, sine of 90 is going to be equal to sine of 90 is going to be equal to opposite over hypotenuse. So it's going to be equal to opposite over hypotenuse, but then the opposite and hypotenuse are similar. So sine of 90 is going to be 1, dividing equal numbers, and then cos of 90. Remember that the adjacent becomes 0, so this is adjacent over hypotenuse, but the adjacent becomes 0, so the hypotenuse becomes this, and then this becomes 0. And then we look at the tangent of 90, tan of 90. Tan of 90 becomes adjacent over, becomes opposite over adjacent side to that angle that we're referring to. And then this becomes opposite of adjacent. It becomes, excuse my writing, no, it's bad. It becomes, this opposite here is a value, so you do have the opposite side, and then adjacent is 0. And then you do have the adjacent as 0. Now if you divide a number by 0, that spikes up to, it gives you an error. In a sense, it's more like infinite. You're saying how many nothings are there into something. Well, there are infinitely many. You can argue that, but we'll look more when you look in number classification and on what dividing by 0 or what it actually means. And when we look at also power rules and all that, because we're going to also look at exponentials. When you look at exponential, we'll explain all those, what happens when you power to the power of 0, and how do you get to the conclusion or the axiom that we develop when you power to the power of 0, or what happens when you divide by 0. But then if you press this on a calculator, tan of 90 is going to give you an error because it can't define that. In a sense, to me, it's possible that it's infinity, because how many nothings are there in something? You could say the infinitely many intuitively, or you could say, well, that question is rubbish, I cannot answer it. So in a sense, that's the case. So now from this we have developed something very nice for these two angles. Now we know that for these two angles, we have our trig ratios, and then we have angles. So we have angle, oh god, excuse me, we have our trig ratios, then we have the angle, and then so we have our trig ratios, and then we have the angle, and then the angle will be divided into two sections, and then we will have our trig ratios this side. So the trig ratios are, we have sine, then we have cos, then we have the last one, which is a tangent. We have a tangent, And then here we have the angle theta, which is equal to 0, and the angle, oh sorry, what am I doing here? Here's what we're going to do, that's fine. Delete this, and then we can delete that angle there. It's fine also. So we can remove that angle there and to make a nice table here, because this introduces us to a new concept that we're going to be looking at after that. So we're going to say angle this side. Yeah, this is perfect. Angle here. And then the angle here is theta is equal to 0 and theta is equal to 90. Nice. Then we have our evaluations here. So we say sine of theta, when theta is equal to 0, that is also what? We said that is also 0 from our analysis here. We said that is also 0, and in the cosine we said it's 1, and this here we said it's 0. And then in the cotangent, so this is 1, we said this is 0, and we said this here becomes an error, or it goes into infinity. So you get the idea now. This is now a table of two special triangles. Now you'll see what we mean by special. Sorry, this is a video of two special angles. You know, we have infinitely many angles that you can get in a triangle. They could be 61 by 29 and then 90. They could be 63 they could be 70 by 20 then 90. There could be many, infinitely many. As you can see, there could be 50 by 40 and then 90, as long as they sum up to 180 and one angle on that triangle is 90, because that's what we're dealing with. Then these are special case holds, and we have these special angles that we have here. Now I just wanted to show you how can we make evaluations. If remember, when we were looking at similar triangles and developing these tricks, we made evaluations from the actual we made evaluations from the actual ratios and defined these from ratios. Now I want to define these ratios, but defining them using angles. So there's special algorithms and special intuitive reasonings that you can use to do that. Your calculator does that because you can move from an angle and get the ratio of that angle. You know, in a sense, you can, even in a computer, you can store almost all the values for all the different angles. And then your computer will just know that, well, whenever the angle is 0, it doesn't matter how big my triangle is, whatever it is, whenever that angle is 0, what I'm supposed to get is this value, because that value is consistent, which is what we're talking about when we're talking about similar triangles. So that's how these calculators and things will evaluate those things. And then, of course, there's different algorithms and ways of evaluating. Because when you're doing it from a triangle and using, and measuring this, which is what we're doing in the other video, is easier. But when you now want to convert from an angle back into something else, then it becomes problematic. Also, one thing that I wanted to highlight is that with these ratios here, these ratios are very, very, very special. These ratios here, that's one thing that I also wanted to highlight. These ratios here are very, very special because this triangle here, the format of this triangle is a very special format. But we are going to look at it further. For now, I just wanted to give you those. And then when we go deep into it, we're going to look at it further and why it's so special. For now, I just didn't want to talk about it. So that's going to be it, and I hope you enjoyed this video. If you have any questions, ask me. If you want to get further, you can go revisit my previous videos and just get a sense of flow into the development of these concepts.